Chapter 5, Section 1. In this chapter, Section 1, we'll be looking at accumulated change. So let's say you're driving along in your car at 60 miles per hour for 4 hours. If at that point you wanted to know how far you had driven, you would simply multiply your miles per hour, which is 60, times the number of hours you had driven, 4, and you would know that you had traveled 240 miles. This uses the fact that distance equals velocity times time. Velocity is a rate at which something is traveling. What we're doing here is we're finding a total area. Graphically, what it would look like, you see the graph below, we have a rate on the y-axis and we have a time on the x-axis. By finding the area underneath that line, we find the total distance traveled. What would happen if you had differing velocities? So let's say now that you start driving and you go 10 miles per hour for the first hour, 20 miles per hour for 30 minutes, and then 30 miles per hour for an additional 2 hours. Then how far did you travel? Well, we can't just multiply two numbers now. We have to break it up into different intervals. So we would do 10 miles per hour times 1 hour for that first piece, plus 20 miles per hour times 0.5 hours, which would represent 30 minutes, plus 30 miles per hour times 2 hours. When we add those all up, we get 50 miles. When velocity is not constant, we want to break it up into each individual interval, multiply together, and add. So how do we measure accumulated change? Well, let's say that we want to do an experiment where we're going to measure your velocity every 10 minutes in feet per minute. If I wanted to know how far you traveled over 30 minutes, how could we calculate this? Well, looking at this table, we don't know exactly how long we are at any given velocity before it begins to increase. So the best we can do is estimate. There's two different estimations that we will learn. Let's start with what's called a left-hand estimation. That will be abbreviated by LHE. When you look at the table, the first thing you want to notice is what the time intervals are. So here we're counting by tens because we're checking every 10 minutes. So when we do a left-hand estimate, we look first on the left-hand side and start with the 0, 0. We look at the first time interval, 0 to 10. Over that first 10 minutes, the velocities range from 0 to 4. Well, we don't know what it is at most of the time, so we pick the leftmost velocity to use for our measurement. So we do the first 10 minutes, 10 is our time, and the rate we're going to use is the one on the left, which is 0. So we do 10 times 0. Plus, then we look at our next time interval, which is 10 to 20. Again, that's another 10 minutes. That's our time interval, 10 to 20. So that's our time, and we need to multiply that by a rate. So again, there's two rates, 4 and 10. We pick the one on the left because we're doing a left-hand estimate. So we have 10 times 4. And then lastly, for that last chunk of time, we look from time 20 to time 30. So from 20 minutes to 30 minutes, that's another 10 minutes. So time interval here is 10. And we'll pick the velocity on the left of the two underneath, which is 10. So we do 10 times 10. We add those all up, and we get 140 feet. However, when we do a left-hand estimate, you can see that we neglect to use the 18, and we can't just leave it out altogether. So we have something else that's called a right-hand estimate. And as you can imagine, it's going to work similarly to the left-hand estimate, only we'll begin on the right. So when we start on the right, we start with the last 10 minutes. So we look between 20 and 30, because we're starting on the right, and we say, okay, that's a time interval of 10 minutes, and that's our time. We're going to multiply that by our rate, and we're going to pick the rate of the two that's on the right. So we're picking the 18. So we have 10 times 18. Then, from time 10 to time 20, we want to multiply that 10 minutes times the rate on the right, which is 10. And then, from time 0 to time 10, that's 10 minutes. We multiply that 10 minutes times the rate on the right, which is 4. And we add those all up, and we get 320 feet. Well, you can see that 140 feet and 320 feet are very different. So what do these numbers mean? Well, those numbers will give us bounds on the actual distance traveled. So what we can now say with confidence is that the actual distance that we traveled during this experiment has to be bounded by 140 and 320. The larger number is known as the overestimate, and the smaller number is called the underestimate. More accurately, let's say we wanted to make it a little more accurate. We could repeat this experiment and calculate it every 5 minutes instead of every 10. So now I've created a new table, which I would have gotten from an experiment, and we'll calculate the left-hand estimate and the right-hand estimate every 5 minutes. So here, if we do the first 5 minutes starting with the left-hand estimate, the time intervals are now by 5s. So from time 0 to time 5 is 5 minutes, times the rate on the left, which is 0. So we have 5 times 0, plus from time 5 to time 10, that's another 5 minutes, and we'll multiply that by the rate on the left, which is 2. From time 10 to time 15, that's another 5 minutes, multiplied by the rate on the left, which is 4. Time 15 to time 20, multiplied by the rate on the left, which is 7. Time 20 to 25, another 5 minutes, multiplied by the rate on the left, which is 10. And from time 25 to time 30, that's another 5 minutes, and we multiply by the rate on the left, which is 14. Add those all up, and you get 185. Similarly, we want to find the right-hand estimate. So we start on the right hand of the table, and again we work our way back in a similar fashion, starting with time 25 to 30, which is 5 minutes. We take the rate on the right, which is 18. We work our way back, and our right-hand estimate will work out to be 275. So again, the actual distance traveled will have to be bounded by the numbers we found, where the left-hand estimate is 185, and the right-hand estimate is 275. So now you can see that our bounds are a little bit more stringent. So what this means is that you get a better approximation the more often you calculate. So if you can get the time interval even smaller, you'll get an even better approximation. Consider the following table, where we're going to count by 2's, 2, 4, 6, 8, 10, every 2 seconds. And we have velocities measured here. If we were to do a left-hand estimate, you would get 360 feet, and a right-hand estimate would give you 420 feet. What I want to show you is what this is doing graphically. So you have some velocity function, which is represented by the line. When you do a left-hand estimate, you get what you see in the blue color here. So you get these rectangles. You're going up until you hit the graph, and then you come over and down to the next time interval. You're making an approximation by rectangles by taking the area of each of these and adding them all together. When you do a right-hand estimate, you start on the right, and what you'll get is the blue rectangles, and in addition, also the white rectangles that are on top. So you get that whole entire thing. So you'd be working backwards, and you can see that one is an underestimate and one is an overestimate of the exact area under the curve. Well, that's sort of the goal here, to find the exact area under the curve. So what does this mean graphically? Well, let's look at something where we have t equals 1. So we're calculating it every 1 second. You can see the rectangles drawn in. If we then went ahead and calculated the same graph every half second, you can see that now the rectangles much more closely resemble the actual graph. And then if you went ahead and did every quarter second, we're almost exactly under the graph, where you can see the last graph given as the exact area under the curve. In general, to get the total area under a curve, we'll be looking at a rate times a time. We want to get the best approximation that we can to get this area under a curve, because this will give us a total, either population or size of something, and that's sort of the goal overall, because what we're doing is we're taking a rate and we're going back to the original function. Remember that if we have a table, this is going to give us bounds on the actual area under the curve. So work with these left-hand estimations and right-hand estimations, and go ahead and try the first homework from Chapter 5.